In this video, I am going to explain about types of network automation and after that data-driven type. In future videos, we will learn about the other types of network automation. About the automation, you know that automation has taken the world of networking by storm in the past couple years. The speed and agility automation provides to companies is unprecedented compared to the old way of doing things manually. In addition to speed, automation can bring many other benefits to networking, such as consistency in actions and reduction of human errors. Automation can be applied to many different processes and technologies in different ways in the world of networking. In this video, when we refer to network automation, we are referring to the process of automatic management, configuration, testing, deployment, and operation in any kind of network environment, either on premises or in the cloud. This video approaches automation by subdividing it into the following types and providing use cases and tools for each of them. First, data-driven automation, task-based automation, and end-to-end automation. This division is not an industry standard, but is a reflection of the most commonly seen outcomes from the network automation. This figure provides an overview of the use cases described for each of these three types of automation in this video. First, data-driven, second, task-based, and finally, end-to-end. About the examples of data-driven, we have monitoring devices. I will explain them in this video. And also compliance checking, and then optimization, and then predictive maintenance, and finally, troubleshooting. Also about the next type of automation, task-based automation, we have some use cases like the migration, configuration, provisioning, and testing. Now let me to explain about data-driven automation. Everyone is talking about data automation, folks included. Data is undoubtedly among the most important components in a system. But what is actually data? Data is facts or statistics collected about something. Data can be used to understand the state of a system, used to make decisions based on reasoning and or calculations, or stored and used later for comparisons among numerous other possibilities. The possible insights derived by analyzing data make data an invaluable asset also for networking automation's solutions. What data-driven automation is? Data-driven automation can be involves automating actions based on data indicators. As a simple example, you could use data-driven automation to have fire sprinklers self-activate when the heat levels are abnormally high. Data-driven automation is the prevailing type of automation in the networking world. Firewalls can be configured to block traffic, this is action, from non-client or non-compliant endpoints, compliance data. And monitoring system can trigger alarms, action based on unexpected network conditions such as high CPU usage on networking equipment, this is the metric data. Data-driven automation can take many shapes and forms, but it always starts from data. Data can be expressed in many formats, and for example, there are push and pull models in data-driven automation architectures. In push models, devices send information to a central place. The sensors in the left figure, for example, can show us actually the sensor sends measurements to the management stations, which receives them and can take action based on those readings. Example of networking protocols that use a push model include syslog, net flow, and SNMP trap. And also here we have pull model. Pull models are the opposite of push models. In a pull model, the management station pulls the sensors for reading and can take action based on the result. A networking protocol that utilizes a pull model is SNMP polling. To better understand the difference between these two models, consider a real-life example involving daily news. With the pull model, you would go to a news website to read news articles. In contrast, with the push model, you would subscribe to a news feed, and the publisher would push a notification to your phone as news stories are published. Push models are popular today because they allow for faster action, as you don't have to pull data at a specific time. Okay, in future, we will cover model-driven telemetry, which is an example of a push model. Modern push protocols allows you to subscribe to a specific information, which will be sent to you as soon as it is available or at configurable fixed time intervals. However, in some use cases, the pull model is preferred, such as when the computing power available is limited or there are network bandwidth constraints. In these cases, you would pull only the data you think you need at the time you need it. The problem with the pull model is that it may not always give you the information you need. Consider a scenario in which you are polling a temperature measurement from a network device. Failing to poll it regularly or after an event that would increase it could have disastrous consequences. You have probably been using data-driven automation for years. The following sections guide you through use cases for adding automation to a network. Now let me to explain about data-driven automation use cases. Even if they don't use the term automation, companies use data-driven automation all the time. There are opportunities for automation in many IT processes. The following sections describe some use cases for data-driven automation. Later in this course, you will see use case or case studies of some of these use cases transformed and applied to global scale production systems. First, monitoring devices. This is the first data-driven automation use case. One of the quickest and easiest ways of getting into automation is by monitoring device configuration or metrics. Monitoring device metrics is a well-established field, and you can use a number of tools that can collect network statistics and create dashboards and reports for you. We will learn about some of these tools in future in this course. In addition, you can easily create your own custom solutions. One of the reasons to create your own tools is that off-the-shelf tools often give you too much information and not necessarily the information you need. You might need to build your own tool, for example, if you need to monitor hardware counters, because industry solutions are not typically focused on a specific detailed implementation. By collecting, parsing, and displaying information that is relevant for your particular case, you can more easily derive actionable insights. Monitoring device configuration is just as important as device metrics, as it prevents configuration drift, a situation in which production devices configuration change so that they differ from each other or from those of backup devices. With the passing of time, point-in-time changes are made to deal with fixes or tests. Some of the changes are not reflected everywhere, and thus drift occurs. Configuration drift can become a problem in the long run, and it can be a management nightmare. The following are some of the protocols commonly used in network devices monitoring: Simple Network Management Protocol (SNMP) and Secure Shell Protocol (SSH), and NetFlow and syslog. Here you can see SNMP is used for metrics and secure SSH for configuration, NetFlow metrics, and syslog also metrics. Each of these protocols serves a different purpose. For example, you might use SNMP to collect device statistics such as CPU usage or memory usage, and you might use SSH to collect device configuration. Okay, and in future you look more closely at how to collect data and which method to use. Automation network monitoring or automating network monitoring tasks does not simply add speed and agility, but allows networking teams to get updated views of their infrastructure with minimal effort. In many cases, automating network monitoring reduces the administrative burden. To put this into perspective, let's look at an example of a network operations team that needs to verify that the time and time zone setting in all its network devices are correct so that logs are correlatable. In order to achieve this, the network operator will have to follow these steps. Step 1. Connect to each network device using SSH or Telnet. Step 2. Verify time and time zone configurations and status. If these settings are correct, proceed to the next device. If these settings are incorrect, apply needed configuration modification. The operator would need to follow this process for every single device in the network. Then it would be a good idea to revisit all devices to ensure that the changes were applied correctly. Opening a connection and running a command on 1,000 devices would take a lot of time, over 40 hours if operators spend 2 or 3 minutes per device. This process could be automated so that a system, rather than an operator, iterates over the device, verifies the time and time zone setting, and applies configuration modification when required. What would take 40 hours as a manual process would take less than 2 hours for automation, depending on the tool used. In addition, using automation would reduce the possibility of human error in this process. Furthermore, the automation tool could later constantly monitor time data and alert you when time is not in sync. From this example, you can clearly see some of the benefits of automation. The process used in the time verification example could also be used with other type of verification, such as for routing protocols or interface configuration. You will see plenty of examples throughout this series of videos of applying data-driven automation using tools such as Python and also Ansible. Now let me to explain about the next use case, compliance checking. Most network engineers must deal with compliance requirements. Systems must be built for regulatory compliance, for example PCI DSS or HIPAA, as well as for company policy. In many cases, compliance checking has become so cumbersome that some companies have dedicated roles for it, with individuals going around monitoring and testing systems and devices for compliance. Today, we can offload some of the burden of compliance checking to automated systems. These systems systematically gather information from target system and devices and compare it to the desired state. Based on the result, a range of actions can be taken, from a simple alert to more complex remediation measures. This figure illustrates a simple data-driven automated flow. Step 1. The management system polls device configuration by using a protocol such as SSH. Step 2. The management system compares the device configuration against predefined template roles. And step 3, the management system pushes a configuration change if the compliance check failed. Automated compliance tools can typically generate reports that keep you aware of the network's compliance status. In addition, integration with other network solutions can help you secure your network. For example, through integration with an endpoint management system, you can quarantine non-compliant endpoints, reducing the network's exposure in the event of a cyber attack. How are you doing your compliance checks today? If you are already using a tool for compliance checks, you are already on the automation train. If you are doing these checks manually, you might consider implementing one of the tools presented in future in this course to help you with the task. The next use case is optimization. Organizations are eager to optimize their networks to make them better and more efficient. Optimization is an activity that we often do manually by understanding what is currently happening and trying to improve it. Possible actions are changing routing metrics or scaling elastic components up and down. Some automation tools can do such optimization automatically. By retrieving data from the network constantly, they can perceive what is not running as efficiently as possible and then take action. A good example of automated network optimization is software-defined wide area networking or SD-WAN. SD-WAN software constantly monitors WAN performance and adjusts the paths used to access resources across the WAN. It can monitor metrics such as latency to specify resources and link bandwidth availability. It is a critical technology in a time when many of the resources accessed are outside the enterprise domain, such as with software as a service or simply on the internet. Imagine that you have two WAN links and your company uses VoIP technologies for critical operations that, when disrupted, can cost the business millions of dollars. Say that you configure a policy where you indicate that packet loss must be less than 3% and latency cannot exceed 50 milliseconds. An SD-WAN controller will monitor the WAN links for predefined metrics and compare them to your policy. When the controller detects that your main WAN link is experiencing poor performance for voice traffic, it shifts this type of traffic to your second link. This type of preventive action would be considered an optimization. As another example of optimization, say that you have some tools that gather the configurations from your network devices and systems. They compare them to configuration best practices and return to you possible enhancement or even configuration issues. Optimization tools today can even go a step further. They can also collect device metrics, for example, link utilization, client density, and compare them to baselines of similar topologies. These tools can, for example, collect data from several customers, anonymize that data, and use it as a baseline. Then, when the tool compares device metrics against the baseline, it might be able to produce insights that would otherwise be very difficult to spot. The next use case is the predictive maintenance. Isn't it a bummer when a device stops working due to either hardware or software issues? Wouldn't it be nice to know when something is going to fail ahead of time so you could prepare for it? With predictive maintenance, you can gather data from your network and model systems and attempt to predict when something is going to break. This involves artificial intelligence, which is a subset of automation. Predictive maintenance is not magic, it's just pattern analysis of metrics and logs to identify failure events. Take as an example, for example, router fans. By collecting rotation speed over time, see this table, you might find that before failing or before failure, rotor fans rotate considerably more slowly than they do when they are brand new. Armed with this information, you could model a system to detect such behavior. In this table, you can see rotor fan rotation per minute or RPM. Predictive models typically use more than one parameter to make prediction. In machine learning terms, the parameters are called features. You may use many features combined to train predictive models. For example, fan RPM, system temperature, device syslog data. Such a model takes care of prioritizing the relevant features in order to make correct predictions. Bear in mind that modeling such prediction systems require a fair amount of data. The data needed depends on the complexity of the use case and the algorithm used. Some models require millions of data points in order to show accurate predictions. Predictive maintenance is still in its infancy. However, it has been showing improved results lately thanks to increased computing power at attractive prices. You will see more on machine learning techniques to achieve this sort of use case in future. Another prediction example is load prediction, which can be seen as a type of maintenance. Some tools collect metrics from network devices and interfaces and then try to predict whether a link will be saturated in the future. Say that you have a branch site with a 1 gigabit per second link to the internet. Depending on the time of the day, the link may be more or less saturated with user traffic. Over time, users have been using more external resources because the company has adapted software as a service. You could use a tool to constantly monitor this link's bandwidth and get warnings when you might run into saturation on the link. Such warnings would provide valuable insight, as you would be able to act on this information before you run into the actual problem of not having enough bandwidth for users. The next use case of the data-driven automation is troubleshooting. Network engineers spend a good portion of their time troubleshooting. Common steps include the following. Step 1. Connect to a device. Step 2. Run show commands. Step 3. Analyze the output of these commands. Step 4. Reconfigure features on the device. Step 5. Test for success. Step 6. Repeat step 1 to 5 for each of the other devices you need to troubleshoot. Take a moment to consider how much knowledge you need in order to correlate logs to a root cause or to know what protocol is causing loss of connectivity for a specific user. Now consider that you might need to do this in the middle of the night after a long work day. Automation can lighten the load in troubleshooting. By automating some of the aforementioned steps, you can save time and solve problems more easily. Some tools such as DNA Center already have troubleshooting automation embedded. The way they work is by deriving insights from collecting data and communicating to the operator only the end result. Such a tool can handle the steps 1, 2, and 3, then you, as the operator, could act on the analysis. Step 4 and step 5 could also be automated, but most troubleshooting automation tools are not in a closed-loop automated state, which is a state where the tool collects, analyzes, and acts on the analysis, without any input from a human. Rather, with most troubleshooting automation tools, humans still press that final button to apply the change, even if it's just to tell the tool to apply the change. Sometimes, the only human interaction is a simple confirmation. Visualize the following troubleshooting scenarios. First, reported issues. Applications and users are reporting loss of connectivity. Second, symptoms. Several switches are experiencing high CPU usage. Packet drop counters are increasing. Troubleshooting steps. Collect log message from affected devices by using the show command. Verify log message from affected devices. Trace back activity logs to the time when the problem was first reported. Correlate logs by using other troubleshooting techniques such as, for example, traceroute. After the users report problems, you could follow the troubleshooting steps yourself, but you would need to narrow down the issue first. You could narrow it down by collecting metrics from a network management system or from individual devices. After this initial step, you could troubleshoot the specific devices. While you do all this, users are still experiencing issues. An automated system is more agile than a human at troubleshooting, and it can make your life easier. An automated system consistently collects logs and metrics from the network, and it can detect a problem when it sees values that do not match the expected values. The system can try to match the symptoms it sees to its knowledge base to identify possible signature problems. When it finds a match, it reports discoveries to the network operator or even mitigates them itself. Most tools report findings rather than resolve them due to the criticalism of networks. In this specific scenario, the underlying issue could be that a layer 2 loop, for example, is being by a misplaced cable connection. Receiving a notification of a possible layer 2 loop is much more helpful and actionable than hearing that some users are reporting loss of connectivity. This example illustrates the real power of automation, enabling and empowering people to do a better job. Keep in mind that with troubleshooting automation, it is crucial to have a good knowledge base. Without such a knowledge base, deriving insights from collected data will not be effective.